looks like the simplest object in any office, but making it involves cooking wood in chemicals hot enough to strip paint. It's thin enough to see light through, yet a single roll of it coming off the production line can stretch for over 20 miles without breaking. And somehow this material that feels almost disposable is manufactured to a tolerance more precise than most people would ever guess. That shouldn't be this complicated for something most of us throw away without a second thought, barely a minute after it served its purpose. So how do factories turn an entire tree trunk into something thin enough to fold, light enough to float, and consistent enough that billions of identical sheets come out the other end every single day without a single visible seam or flaw? Let's step inside and find out. Most people go their entire lives without ever seeing what paper looks like before it's paper. It doesn't start as a sheet or even as pulp. It starts as a log, and by the time it's finished, almost nothing about it resembles where it began. The transformation from solid wood to a smooth, flexible sheet happens in less than a single day, inside one continuous machine that can stretch longer than 2 football fields end to end. Paper begins at a logging operation, almost always using fast-growing softwood trees like pine, spruce, or fir. These trees are chosen specifically because their fibers are long and flexible, which makes for stronger paper later in the process. The logs arrive at the mill by truck or rail, still covered in bark, some over 60 feet long. Before anything else happens, the logs pass through a debarking drum, a massive rotating cylinder that tumbles the logs against each other with enough force to knock the bark completely off, without a single blade touching the wood. The bark itself isn't wasted, it's usually burned to help power the mill. Once stripped, the bare logs are fed into a chipper that reduces an entire tree trunk into small wood chips, each about the size of a postage stamp, in only a few seconds. This is the single raw ingredient that everything else in this process depends on. Not every chip makes the cut either. The chips pass over a vibrating screen that sorts them by size. Pieces that are too large are sent back through the chipper for a second pass, while pieces that are too small or dusty are diverted to be burned as fuel for the mill itself. Only chips within a narrow, consistent size range move forward, because uneven chip sizes later translate into uneven cooking, which means uneven paper. The wood chips are loaded into a massive pressurized vessel called a digester, sometimes tall enough to fit a 10-story building inside it, along with a chemical solution that breaks down lignin, the natural glue that holds wood fibers together. The chips are cooked at temperatures around 170 degrees Celsius for 1 to 2 hours, under enough pressure that the wood essentially dissolves apart at the fiber level rather than being torn apart mechanically. What comes out the other end no longer looks like wood at all. It's a soft, brownish, fibrous material called pulp. And if you ran it through your fingers, it would feel closer to wet cotton than anything resembling a tree. The pulp is washed repeatedly to remove leftover chemicals and any remaining bits of bark or debris, then passed through screens that filter out anything that isn't a usable fiber. At this stage, the pulp is still a dull brown color, closer to a paper bag than a printer sheet. To reach the bright white most paper is known for, the pulp goes through several rounds of bleaching using oxygen, chlorine dioxide, or peroxide-based chemicals, depending on the mill. Each stage strips a little more color out until the pulp reaches close to 90% brightness, a specific industry measurement that determines how white a finished sheet will look under normal light. The bleached pulp, still just a mass of individual fibers, is mixed with massive amounts of water until the mixture is more than 99% water and less than 1% actual fiber. This extreme dilution is necessary because the fibers need room to spread out evenly. Too concentrated, and the finished sheet would be lumpy and uneven. This diluted pulp mixture is sprayed at high speed onto a continuously moving mesh screen called a wire. As the mixture moves along the wire, gravity and suction pull the water downward through the mesh, leaving the fibers behind in a thin, even mat. This is the exact moment where loose fibers first start to become something resembling a sheet. The fibers themselves have no natural adhesive holding them together. There's no glue added at any point in this process. Instead, as the water drains away, the fibers physically interlock with one another, and form weak hydrogen bonds, the same kind of bond that holds water molecules together. It's a strange thing to consider. An ordinary sheet of paper stays in one piece purely because of the same chemistry that makes water droplets cling to a window. The still wet fiber mat, now roughly 60% water, passes between a series of heavy rollers that squeeze out more moisture through mechanical pressure alone. This step alone removes a significant portion of the remaining water without using any heat at all, simply through the physical force of the rollers, pressing the fibers tighter together. Engineers actually prefer removing water this way whenever possible, since pressing water out mechanically costs a fraction of the energy that drying it out with heat would require. Every gallon of water squeezed out here is a gallon. The mill doesn't have to spend fuel evaporating later. The press sheet then travels across a long series of steam-heated cylinders, sometimes dozens of them in a row, each one slightly hotter than the last. By the time the sheet passes over the final cylinder, it has gone from roughly 60% water down to less than 6% moisture, finally becoming true dry paper. In the last stage before the paper is rolled up, it passes through a stack of heavy, smooth steel rollers called a calender. This step compresses and smooths the surface of the paper, giving it the flat, even texture needed for consistent printing. By the time the sheet reaches the end of the machine, it's moving at speeds that can exceed 60 miles per hour, faster than most cars travel on a highway. And it has gone from a solid wood chip to a finished sheet of paper in well under a minute of actual machine travel time, even though the entire mill process from log to roll can take most of a day. Before any roll ever leaves the building, sensors mounted along the entire length of the machine continuously scan the paper for thickness, brightness, and moisture content, adjusting the process in real time. If a section of the sheet runs even slightly too thin, too damp, or too dark, an alarm flags the exact location on the roll so it can be trimmed out before it's shipped. Some mills also run a small sample from every roll through a lab, testing how much force it takes to tear the sheet in different directions, a measurement called tensile strength, to make sure every batch behaves the same way, whether it's headed to a printer, a book publisher, or a shipping label factory. Here's the detail that surprises almost everyone. A single continuous roll of paper coming off this machine, before it's ever cut into individual sheets, can stretch for more than 20 miles, long enough to drive across an entire city without running out of paper. And that roll is often over 20 feet wide before it gets sliced down into the narrow rolls and sheets we actually recognize. One tiny inconsistency in fiber thickness anywhere along that 20-mile length can create a visible defect, which is why paper mills run constant sensors along the entire line, checking thickness down to fractions of a millimeter, thousands of times per minute. And the process is almost entirely self-sustaining. The lignin and other organic material removed from the wood during cooking isn't thrown away. It's burned in the mill's own boiler to generate steam and electricity, which powers many of the machines used earlier in the same process. A modern paper mill can produce more energy from its own waste material than it actually consumes, turning what looks like a straightforward manufacturing line into something closer to a closed loop, where almost nothing that enters the building leaves as true waste. Once the giant master roll is finished, it's transported to a separate part of the mill, where it's sliced into narrower rolls or cut into standard sheet sizes using rotating blades that move with the paper, rather than against it, preventing tears. The finished sheets are stacked into reams, wrapped, boxed, and palletized, ready to sit quietly in a warehouse, a delivery truck, or a printer tray, waiting for the one job it was built to do. From the moment the first log entered the debarking drum to the moment a finished ream gets shrink-wrapped and stacked on a pallet, the entire journey usually takes less than 24 hours. A single day to turn a tree that spent decades growing into a stack of paper that might get used, printed on, and recycled again within a week. That's how a tree, cut down, stripped, cooked, bleached, pressed, and dried across a machine longer than a football field, becomes the sheet of paper sitting in your printer right now. From a solid log to a sheet thin enough to see through, every stage exists for one reason: consistency at a scale most of us never think about. Because the paper only works if every single sheet behaves exactly like the one before it, whether it's the first sheet off the roll or the millionth, until now.